Hi, I am Arun, founder and researcher at Simulatics. It's the AI and numerical simulation startup. I welcome you to the introductory lectures on physics-informed neural network, where we will see the mathematics details of pins, and we also have some hands-on sessions to solve partial differential equations using pins. So I shall briefly share some of my contribution to the physics-informed neural network. So we introduced one novel adaptive weight viscosity pin architecture to solve compressible flows. One of the peculiarity of this scheme is it can able to resolve the shocks on two grid points, which is quite unattainable by any shock capturing schemes which I know. We also introduced one multi-resolution pin which can outperform some of the serial Fortran codes on fine grid. We have shown that physics-informed neural network can act as a physics-based filter to remove noise on high-speed flows. So we know whenever we deal with high-speed flows, we need some sophisticated numerical schemes. So the numerical schemes may become unstable when the data is quite noisy. In that case, pins will be quite handy. Spin is relatively new field. So we have been trying different projects to push the boundary of this field. So with this background, I hope I can give you a solid introduction to physics-informed neural network. I will share some of the advantages and disadvantages of the pins. Now we shall get into the scope and outcome of this talk. So I will provide the mathematics behind the physics-informed neural network. So we also implement uh, pin codes on PyTorch. We also see the possibility to generate the pins code using ChatGPT app Gemini. So some of the equations we'll be solving are heat equations, wave equations, Navier-Stokes equations, and Euler equation. We also see some of the applications of pin for inverse problem. Some of the prerequisites of these talks are, so if you already know the basics of Python and PyTorch, it will be handy because just a theoretical understanding of the pin may not help you. And if you already have some basics of basic methods to solve partial differential equations using analytical numerical procedure, that will be more handy. So when we solve some high-speed flows, we we borrow some of the concepts that already existing in CFD. So that will be quite useful to appreciate the solution procedures using pin. Please note that pins are not the alternative to traditional methods like finite difference, finite volume, or finite element methods. This will be little more handy if you already have a knowledge of those sophisticated numerical schemes. Having said this, we shall move to some of the applications of the pin. First, we shall see some of the applications of pins in fluid dynamics. So pin can handle laminar, turbulent, or even supersonic flows. So we will be having some hands-on session of how to solve fluid flow problems in our upcoming videos. So we can do a shape optimization and we can also do some inverse study. For example, let's say we have a flow data. Let's say that's from PAV. You know, PAV can measure the velocity data. If we are interested in pressure from that PAV data, it's easy to do such kind of process using pin. So this is one of the applications of the pins. So this is a supersonic flow over a wedge case where the inflow Mach number is 10. This is the result taken from our paper. You can refer this paper. We will be solving similar problem in our upcoming videos. The second application is structural mechanics. We shall predict stress, strain, or whatever we can do with traditional CFD methods using pain. We can also do an inverse study. For example, let's say we have a displacement data over the whole field. If you want to find the stress information from that, we can use pin to get it. Or if you're interested in material properties like Young's modulus and other things, it's also possible using pins. We can also detect cracks and other phenomena using inverse problem using pins. So this is one interesting paper you can go through. Another promising application of physics-informed neural network is heat transfer and thermal applications. Similar to CFD, here we can couple the heat equations with the fluid flow equation, or we can solve the heat equation to get the solution of heat equation like temperature or heat fluxes, etc. We can also do inverse study on heat equations. So this is one interesting paper. So another important applications of PINs is medical imaging and ultrasound. You know, the medical equations are governed by some partial differential equation, especially the ultrasound is governed by wave equations. So we can use the wave equation principle to remove noise, or we can reduce the formation or remove the speckles from the ultrasound data. This is one of the emerging field. Apart from that, we can also use that we can do inverse study on ultrasound images like elastography and other stuffs. We can also make a super resolution images. Super resolution means if, let's say our image is 100 cos 100 pixels, we can convert that into 200 cos 200 pixels. That we call a super resolution. So in most of the traditional methods, we use some interpolation methods to do it. But if we have a governing equation or something, we can make a physics-informed super resolution from the data. So this is one interesting paper where they have used pins for inverse study on ultrasound data. Another important application is environmental study and earth and science. So, you know, the weather prediction is very complicated, especially the extreme rainfall event and long-term weather predictions. So those models can be improved or studied using physics-informed neural network, because physics-informed neural networks is borrowed from neural network where we can make a surrogate model. We can also do a sensitive study and such kind of thing. It's relatively easy than conventional methods than when we use physics-informed neural network. So this is one another interesting paper where they have augmented their images using physics-informed neural network. Another important application is robotics and control systems, where we have a governing equation. If you are interested in studying the dynamics of the controller or something, it's relatively easy using these methods. This is one interesting paper you can go through. So having said this, we shall see some of the advantages of the pin. So pins are literally good for transient multidimensional simulations. So one of the advantages of the pins over the traditional method is curse of dimensionality. So we know when we do an 3D simulation, we may have some constraint. So if we use some explicit methods, we may have a CFL constraint or diffusion number constraint, vector number constraint, those things. So when we go for multidimensional, our computation time exponentially increases. So that's one of the biggest drawbacks of traditional CFD methods. But when we use pins, so these are not a grid-based methods. These are based on collocation-based methods, or uh, these are slightly different approaches. We will see what's the difference between traditional methods and the pins in upcoming videos. So here we need some sampling points. So if you use a latent hypercube sampling procedures, we may a little bit get rid of the curse of dimension. Of course, we cannot completely escape from the curse of dimension when we use pen, but at least we can say they are not that much sensitive like traditional methods. They are literally more stable than explicit numerical schemes. You can refer our paper for this. I have shared the paper in fluid dynamics example. There we have shown how pin can be relatively more stable than explicit numerical methods. So they are literally more robust in designing surrogate model on pure data. So now we shall see what is surrogate model. Surrogate model is nothing. Let's say we have a data we obtain from some numerical simulation or through experimental studies. If we want to make a functional approximation of that data, that we call as surrogate model. So pins are literally more handy to make the surrogate model, especially when we have a limited data. So we know surrogate models are very sensitive to the data points. For example, let's say we have a system equation and we have a lesser number of data. We can ensure that we can make a neural network which satisfies both system equation as well as data. That's the one advantage of the pins over the traditional surrogate models. So implementing code is relatively much more easy when compared to traditional methods. Of course, in these lectures, we will see how to solve even supersonic flows using pins. But if you use traditional methods, that's a very lengthy procedure. For example, if we want to solve supersonic flows, we should know what kind of Riemann solvers or artificial dissipation scheme we use. We should also see what kind of discretization we use, especially finite volume or finite difference, how to provide upwinding, and we should also care about what kind of time integration we use, because most of the cases Euler may not be good, or shall we go for Runge-Kutta methods or implicit time stepping. So that's a very long code to learn. But in PIN, this is not that much complex. So we shall see how to solve problems using pins. So they are very ideal for inverse study. So this is a forward, I mean, what I explained was a forward problem, but pins are literally more better than forward problem to handle inverse problem. So this will be more handy when our data is very noisy and we have less number of data samples. For example, let's say if we have a geological data, it's very difficult to get those data. So we may use some ultrasound signals, RF images to get it. Those are relatively more noisy. Even if we use PAV or those kind of techniques, if our correlation procedures or seeding particles is not good, we may get a very noisy data. In that case, we can improve the images using basis informed neural network. So another important advantage is this vanilla pin is free from numerical discretization and truncation error. Of course, this is not a complete statement. Anyway, in future, I will dig this into more deeper. For example, when we use the numerical methods, we have to take care of a lot of stuff, especially discretization. For example, if we solve wave equation, we should ensure whether we have provided proper upwinding. If we didn't provide any upwinding, the numerical scheme may fail. But we no need to care of such kind of issues when we solve problems using pins. Another important advantages of the pin is, so pin provide the space-time solution. But if we solve problem using traditional methods, first thing what we'll be here doing is first we will decouple the space and time. So let's say we are solving some wave equation, we will be convert the ordinary differential equation to PDE. That approximation we call the method of line approximation. Then we solve in space, then we march in time. So like that we go. And output of the pin is continuous function. But if you take the numerical methods, they are only known at the cells or points. In addition to that, pin is meshless method, so we no need of mesh connectivity information. A pin are relatively less sensitive to overfitting than traditional A&M-based surrogate model. Of course, we cannot say this pin is completely escaped from overfitting because pins are based on collocation points. Sometimes the results of the pins are subjected to the distribution of the collocation points. Having said these advantages, pins also come with a lot of disadvantages. Now we shall see some of the challenges and disadvantages of the pins. The pins are literally computationally more expensive when compared to traditional methods because they are based on optimization procedure. Of course, traditional methods, we have both iterative methods and non-iterative methods. Sometimes the iterative methods may be expensive. In addition to that, pins where we need a lot of tinkering and tuning because here we have a lot of neural networks, neurons, layers, hyperparameters like learning rate, etc. So we don't know which is a suitable one what for our case. Of course, of course, that universal function approximation guaranteed there is some solution, but does not say how many number of neurons or how many number of layers or which activation functions we should use to solve the problem. Anyway, we will see what is activation function, what is layer, what is neuron in the upcoming slides. In most of the optimization procedures, we always use gradient-based optimization algorithms. So we know the gradient-based algorithms likely to end up in local minima if our objective function is not convex optimization. Of course, somebody may claim that Adams or momentum-based optimization algorithms may escape from this local minima or maxima based on the learning rate and other cutoffs that we provide. But there is no guarantee that they always give a global minimum or maximum. That's one of the disadvantage of the gradient-based algorithms. Of course, pins also where we also use some gradient-based algorithm, we may likely to end up in local minima. And we may end up in multiple solution if our boundary and initial conditions are not properly selected. So being a new method, it has to come across several challenging problems. We have been trying paints on various challenging problems, but still Pin didn't see very challenging problems like traditional CFD methods. Sometimes we may have some convergence issue if we didn't pick that right neural network architectures or if we didn't tune the tuning parameters, etc. In addition to that, they need expensive GPUs to solve multidimensional problems.